Hello, I'm in the Pilot's Handbook of Aeronautical Knowledge. I'm in Chapter 4. This will be 4-22. This will be stalls. Stalls. An aircraft stall results from a rapid decrease in lift caused by the separation of airflow from the wing surface brought on by exceeding the critical angle of attack. A stall can occur at any pitch, attitude, or airspeed. Stalls are one of the most misunderstood areas of aerodynamics because pilots often believe an airfoil stops producing lift when it stalls. In a stall, the wing does not totally stop producing lift. Rather, it cannot generate adequate lift to sustain level flight. Since the coefficient of lift increases with increase in angle of attack, the amount of the point the coefficient of lift peaks and then begins to drop off. This peak is called the coefficient of lift max. The amount of lift the wing produces drops dramatically after exceeding the coefficient of lift max, or critical angle of attack. But as stated above, it does not completely stop producing lift. In most straight wing aircraft, the wing is designed to stall the wing root first. The wing root reaches its critical angle of attack, first making the stall progress outward toward the wing tip. By having the wing root stall first, aileron effectiveness is maintained at the wing tips, maintaining controllability of the aircraft. Various design methods are used to achieve the stalling of the wing root first. In one design, the wing is twisted to a higher angle of attack at the wing root. Installing stall strips on the first 20 to 25% of the wing's leading edge is another method to introduce a stall prematurely. The wing never completely stops producing lift in a stalled condition. If it did, the aircraft would fall to the earth. Most training aircraft are designed for the nose of the aircraft to drop during a stall, reducing the angle of attack and installing the wing. The nose down tendency is due to the center of lift being after the center of gravity. The center of gravity range is very important when it comes to stall recovery characteristics. If an aircraft is allowed to be operated out of the center of gravity, the pilot may have difficulty recovering from a stall. The most critical center of gravity violation would occur when operating with a center of gravity which exceeds the rear limit. In this situation, the pilot may not be able to generate sufficient force with the elevator to counteract the excess weight aft of the center of gravity. Without the ability to decrease the angle of attack, the pilot or the aircraft continues in a stall condition until it contacts the ground. So yeah, picture that with the weight of the tail, weight behind the center of gravity, the tail is just weighted way down since there's weight back there, and so the nose up, and then all of a sudden you can't produce enough thrust to get enough speed, to get enough lift, and then you stall. The stalling speed of a particular aircraft is not fixed for all flight situations, but a given aircraft always stalls at the same angle of attack regardless of airspeed, weight, load factor, or density altitude. Each aircraft has a particular angle of attack where the airflow separates from the upper surface of the wing and the stall occurs. This critical angle of attack varies from 16 degrees to 20 degrees depending on the aircraft's design, but each aircraft has only one specific angle of attack where the stall occurs. There are three flight situations in which the critical angle of attack can be exceeded: low speed, high speed, and turning. The aircraft can be stalled in straight and level flight by flying too slowly. As the airspeed decreases, the angle of attack must be increased to retain the lift required for maintaining altitude. The lower the airspeed becomes, the more the angle of attack must be increased. Eventually, an angle of attack is reached which results in the wing not producing enough lift to support the aircraft, which starts settling. If the airspeed is reduced further, the aircraft stalls. Since the angle of attack has exceeded the critical angle and the airflow over the wing is disrupted. Low speed is not necessary to produce stall. The wing can be brought into an excessive angle of attack at any speed. For example, an aircraft is in a dive with an airspeed of 100 knots when the pilot pulls back sharply on the elevated control. Gravity and centrifugal force prevent an immediate alteration of the flight path, but the aircraft's angle of attack changes abruptly from quite low to very high. Since the flight path of the aircraft in relation to the oncoming air determines the direction of the relative wind, the angle of attack is suddenly increased, and the aircraft would reach the stalling angle at a speed much greater than the normal stall speed. The stalling speed of an aircraft is also higher in a level turn than in a straight and level flight. Centrifugal force is added to the aircraft's weight, and the wing must produce sufficient additional lift to counterbalance the load imposed by the combination of the centrifugal force and weight. In turn, the necessary additional lift is acquired by applying back pressure to the elevated control. This increases the wing's angle of attack and results in increased lift. The angle of attack must increase as the bank angle increases to counteract the increasing load caused by centrifugal force. If at any time during a turn the angle of attack becomes excessive, the aircraft stalls. At this point, the action of the aircraft during a stall should be examined. To balance the aircraft aerodynamically, the center of lift is normally located after the center of gravity. Although this makes the aircraft inherently nose-heavy, downwash on the horizontal stabilizer counteracts this condition. At the point of stall, when the upward force of the wings lift and the downward tail force cease, the unbalanced condition exists. This allows the aircraft to pitch down abruptly, rotating about its center of gravity. During this nose-down attitude, the angle of attack decreases and the airspeed again increases. The smooth flow of air over the wings begins again, lift returns, and the aircraft is again flying. Considerable altitude may be lost before this cycle is complete. Airfoil shape and degradation of the shape must also be considered in the discussion of stalls. For example, if ice, snow, and frost are allowed to accumulate on the surface of an aircraft, the smooth airflow over the wing is disrupted. This causes the boundary layer to separate at an angle of attack lower than that of the critical angle. Lift is greatly reduced, altering expected aircraft performance. If ice is allowed to accumulate on the aircraft during flight, the weight of the aircraft is increased while the ability to generate lift is decreased. As little as 0.8 millimeters of ice on the upper wing surface increases drag and reduces aircraft lift by 25%. Pilots can encounter an icing in any season anywhere in the country at altitudes of up to 18,000 feet and sometimes higher. Smaller craft, including commuter planes, are most vulnerable because they fly at lower altitudes where ice is more prevalent. They also lack mechanisms common on jet aircraft that prevent ice buildup by heating the front edges of the wings. Icing can occur in clouds anytime the temperature drops below freezing, and supercold droplets build up on an aircraft and freeze. Supercold droplets are still liquid even though the temperature is below 32 degrees Fahrenheit or 0 degrees Celsius. So we'll hold off there. That was stalls. That was page 422 and 423 in the Pilot's Handbook of Aeronautical Knowledge. See ya.